because of the safety discussion. There's no safety discussion at the beginning of this one, but in a lot of the labs there are. And so I was talking about element plus element combination reactions. And so if it's fixed charge, it's easy. If it's variable charge, then we have some choices. So this is variable charge, carbon. So we're going to have some choices. You know, what's carbon's charge in carbon monoxide? 2 plus. In carbon dioxide? 4 plus. What does carbon's charge range from? Carbon's charge ranges from +4 to -4. That's good. And so if we have a hydrocarbon like this, we can burn it. What we're going to do is we're just going to assume that the conditions are right to make carbon dioxide. How about carbon trioxide? No. And so what forms? Can you tell me, in theory, like let's say I don't want any carbon dioxide, I want all carbon monoxide. Can you tell me in theory how I should do that? Okay. Or let's say I want 75% carbon monoxide, 25% carbon dioxide. Can you tell me how I should do that? Do you think the theory is pretty easy regarding that? It's just, you know, just punch it into Google and then it'll spit it out. Do you think so? No. And so a lot of these redox reactions are just done by trial, you know, by experiment. And so what you do is you just do it under a whole bunch of conditions. And then you see under what kind of conditions do you form a lot of carbon monoxide, under what kind of conditions do you form a lot of carbon dioxide. Right? Obviously, we'd like to predict these types of things, so we want to know as much theory as possible. But for right now, we're just looking at this experimentally. And so we got to just pick the right conditions. So it depends on the conditions. We pick the right conditions such that we form carbon dioxide and H2O liquid. We call this complete combustion. This is carbon dioxide gas. This is a gas here. And so this would be a hydrocarbon combusting. We could also have CXHYOZ. CXHYOZ. These could be carbohydrates. They could be alcohols. They could be a whole bunch of things. But all of them burn to form CO2 and water. And so let's do one example of this. Let's take a look at ethanol. If we look at ethanol, C2H5OH. C2H5OH is ethanol. But what I'm going to do is I'm going to combine it. So let's go C2H6O. It's the same formula. But if I look at this, can you tell me what the charges are here? You know, not that these are ions, but what's a typical charge on hydrogen? +1. Okay, what's a typical charge on carbon? Well, it might be +4 or it might not be +4. Carbon is variable charge, but is hydrogen really variable charge, or does hydrogen pretty much stick to one charge? It sticks to one charge. How about oxygen? -2. And so if hydrogen is +1 and we have 6 of those, we have a total positive charge from hydrogen of +6. If oxygen is -2 and we have 1 of those, then we have a total negative charge of -2. All right, all of these charges have to add up to 0. Next slide, I shouldn't. All these charges have to sum up to 0. And so what we have is we have 2 carbons, 2 times the charge on carbon. And so the charge, we'll just call it x times 2. 2 times x plus 6 minus 2 is equal to 0. So what is x? -2. And so the carbon's at a -2. Well, carbon can range from -4 to +4. So what we say is here. So carbon's going to go from -2. Now what we're going to do is we're going to combust this with oxygen. So we have C2H6O. Ethanol is a liquid, plus O2 gas. is going to produce CO2. Yeah. And so our carbon is going to go from -2 to +4 in this reaction. So in order to go from -2 to +4, what must happen? It's got to lose electrons. What's going to happen? Do you know how many electrons it's got to lose? To go from a charge of -2 to +4, how many electrons has to be lost per carbon? Six electrons lost per carbon. We got 2 carbons, so altogether 12 electrons are going to go somewhere. Where do those electrons go? Well, we'll see. And so the other product is water. And so let's balance this. I have 2 carbons here. I need 2 CO2s. I have 6 hydrogens. I'll need 3 waters. And that's going to give me 4 oxygens here plus 3. 4 plus 3 is 7 oxygens on the right. And then I have 1. 1 plus how many gives me 7? 1 plus 6. So I'll need 3 here. And so I'll have 3 O2s. 3 O2s gives me a total of 6 oxygens. Each oxygen wants how many electrons? Oxygen wants how many electrons to form oxide? This is dihydrogen monoxide, carbon dioxide. Oxide has how many electrons? Oxide itself, the oxide ion has 2. And so the electrons, those 12 electrons will go here. We'll talk about this more as we go along, but that's an example of a combustion reaction. So if we have a hydrocarbon or a carbohydrate, alcohol, ether, something with CHO, then we got combustion. Combustion is another example of redox reactions. Redox reactions essentially are just what we call electron transfer reaction. So somebody loses, somebody gains electrons. So when we burn carbon in oxygen to form carbon dioxide, carbon loses, oxygen gains electrons. All right, that's combustion. The next type of reaction that's covered in the book is called single replacement. Single replacement has the form A plus BX. A plus BX yields AX plus B. A is an element. BX, this is a compound. AX is a compound, and B is an element. Okay, this is a redox reaction. Redox reactions, I'm going to start talking about some of the jargon that redox will use. In redox, we have electron transfer. Electron transfer from what we call the reducing agent to the oxidizing agent. From RA stands for reducing agent, to OA stands for the oxidizing agent. And so the element here has no charge here. And then if we form a compound, then that element gains a positive charge. We'll just call it positive X. And X has a negative charge on that. And so what happened here is A went from a neutral charge or 0 charge to a positive charge. So it loses electrons. If it loses electrons, then we call A 0 the reducing agent, RA, reducing agent. So where did those electrons go? Those electrons had to go somewhere. And the electrons went here. We have B plus X, X minus X. The charges might vary. But B plus X goes from positive to the element, which is B0. And so to go from a positive charge to a 0 charge, this gained electrons. So gains electrons here. Loses electrons, gains electrons. And so B took electrons. Whatever species takes electrons is called the oxidizing agent. So oxidizing agents take electrons, reducing agents lose electrons. oxidizing agent. And we'll call that an OA. X is a spectator. This is a spectator. So let's do an example reaction here. We're going to just take some zinc and react it with HCl. And so this follows the A plus BX pattern. A plus BX yields AX. And so if we take zinc, and we're going to form AX, which would be zinc chloride. What's the formula for zinc chloride? Is zinc fixed charge or variable charge? Fixed charge, and what's the charge on zinc? 2 plus. So this is going to form ZnCl2. And then we're going to form B. Well, the B is the element hydrogen. What's the formula for elemental hydrogen? H2. H2 is a gas. Zinc chloride, is that soluble or insoluble? It's soluble. This is aqueous. This is aqueous. And to balance this, we'll need 2 HCl's. Now we look for a driving force. The driving force for single replacement is called the activity series. The activity series looks like this. Activity series, this is the reducing agent strength. So at the top is lithium. This is the most active. And it's active in terms of just reducing agent strength. And so the most active, strongest reducing agent. That's lithium. At the bottom of this list, we're going to have fluoride. This is the least active. And so it's the worst reducing agent, or weakest reducing agent. All right, and then we have different metals. And so we look at the trends here. We look at the trends, and it looks like the group 1 metals are really active. Group 1 metals are really active. They're good reducing agents, which means that they give up their electrons pretty easily. And so the more easily they lose electrons, the better the reducing agent strength they're going to have. So we'll have group 1. There's going to be some overlap with group 2. And then we'll have some like transition metals, transition metals. And then we'll have some noble metals here. Noble metals are very difficult to oxidize. To oxidize means to take the electrons from. And so noble metals are tough. What are some noble metals that you know? Gold. Gold is very tough to take electrons from. Lithium is very easy to take electrons from. Platinum is also very tough. And then we have hydrogen, which is not a metal, but it's in here somewhere. And so the activity series would look like this. It's in your book. And so what we do is we compare zinc and hydrogen. And so let's take a look at this. And so it shows this here. It shows lithium metal here as being the most active in the activity series. And what that means is it's easy to take electrons from. Easy to take electrons, in other words, it's easy to oxidize. So lithium is a metal that's easily oxidized. Gold is a metal that's very difficult to oxidize. And so gold is not very active, lithium is very active. And so the easier it is to oxidize the metal, the higher the activity. The harder it is to oxidize the metal, the lower the activity. We can frame this in terms of reducing agents. Gold is a poor reducing agent, whereas lithium is an excellent reducing agent. Reducing agents give up electrons to the oxidizing agent. And so let's just go ahead and use this activity series to find out if there's a driving force for this particular reaction. And so the reaction is magnesium. We want to compare the magnesium, or not magnesium, what are we doing? Zinc and hydrogen. So we compare the two elements. So we'll compare the activities of the two elements. Activities. Okay, so let's find zinc. Zinc's here. Let's find hydrogen's here. Which one's more active, zinc or hydrogen? Zinc is more active. If zinc is more active, then we're going from more active, zinc, to less active, hydrogen. And therefore, a driving force is present, and we expect this redox reaction to occur. Likewise, what we can do is we could say this. We can say that we're going from a stronger what to a weaker what? Zinc is a stronger what? Reducing agent. So we're going from a stronger reducing agent, SRA, to a weaker reducing agent, WRA. And this chart shows the reducing agent strength. The strongest reducing agent on this chart is lithium. All right, where does the single replacement pattern come from? The single replacement pattern comes from this. If you note that A is the reducing agent, plus B. B plus, this is the actually let's just go BX. BX. BX consists of B plus and X minus. I don't know what the net charge on that is, so let's leave B plus X. Okay, A is your reducing agent, B plus is your oxidizing agent. X minus, this is your spectator. And so what's happening is that A is losing electrons to B plus. In the process of losing electrons, A goes from being the element, which has a zero charge, to being the cation, which has a positive charge. X minus doesn't change. It's just still your spectator. And then B plus goes from being a cation to the element. And so it's gaining electrons. And so it's going from positive charge to a zero charge here. And so all we're doing is we're comparing the direction here. In the forward direction, our reducing agent's A. In the reverse direction, what's our reducing agent? And so if we reverse this reaction, then who loses electrons? B. B loses electrons because it goes from a neutral, zero charge, to a positive charge. And so this is the reducing agent in the reverse direction. And so when we look at the activity series is just comparing which one is a stronger reducing, which one's a weaker. In this case, A is the stronger reducing agent, B is the weaker, so it's downhill going forward. Well, in single replacement, we only look at the reducing agents. We only look at the reducing agents because the oxidizing agents follow the same pattern. And so if this is a stronger reducing agent, then that means that the oxidizing agent here, which is what? What's the oxidizing agent here? H plus. H plus is the oxidizing agent. And what's the oxidizing agent going backwards? Well, if we go backwards, then the oxidizing agent is going to be this. And so if the reducing agents follow this pattern, then the oxidizing agents must, unless I made a mistake. So this is going to be zinc 2 plus, this is our oxidizing agent. And so we compare the oxidizing agents. Well, what do oxidizing agents want? Oxidizing agents want electrons. Reducing agents give up electrons. And so let's take a look at the oxidizing agent chart. Do we have an oxidizing agent chart? And the answer is yes. Because of this. This is the conjugate relationship. If lithium loses electrons easily, that means lithium plus doesn't have a high affinity for electrons. That means lithium plus has low affinity for electrons. Because if lithium plus had a high affinity for electrons, it would grab an electron and hold on to it. And so lithium is a strong oxidizer because lithium ion has low affinity for electrons. That means if lithium ion has a low affinity for electrons, well, taking electrons, that's the oxidizer. And so lithium ion is the oxidizer, and it's a weak oxidizer. And so this is the seesaw or the conjugate relationship. If we have a strong reducer, then its conjugate oxidizer will be weak. How about gold? Does gold want to give up its electrons? No, gold does not want to give any electrons away. That means if it did give up electrons and formed the gold 3 ion, that gold 3 ion is terribly unhappy. If that gold 3 ion is terribly unhappy, it really, really wants electrons. This means that if we have a weak reducer, its conjugate oxidizer will be very strong. And so this is the conjugate relationship. So we only need one chart for both the reducers and the oxidizers. This is the same thing for the acids and bases. A strong acid means a weak conjugate base. A strong base means a weak conjugate acids. Conjugate goes both ways, either way. And so we can see that in terms of oxidizers, gold 3 is the strongest oxidizer on this chart. If gold 3 is the strongest oxidizer, let's find H plus. H plus is here. And then let's find Zn2 plus. Zn2 plus is here. So H plus is a stronger oxidizer than Zn2 plus. And so let's go back to this. So H plus is a stronger oxidizer than Zn2 plus, so it follows. It's got to go strong, strong, weak, weak, or weak, weak, strong, strong. It can't go strong, weak, strong, weak. It has to be paired in this way. And so we only have to look at one. And so this is why in activity series, you only look at the reducing agent. You ignore the oxidizing agent, because it's just easier to look from the perspective of the reducing agent for single replacement reactions. You could see this more easily if we break it up. This is called the complete equation, the CE. But what would the ionic equation for this look like? And so let's take this equation and then figure out the ionic equation for it. The ionic equation, zinc. Zinc solid. Does water break apart the metal in the ionic equation? No. So zinc stays as zinc solid. It's like if you drop a copper penny in water, does it immediately form copper 2, a blue solution? No. So zinc stays solid. What about HCl? Can water break apart HCl molecules? Yeah. In fact, we're going to get 2H plus 2Cl minus. How about zinc chloride? Is that soluble? Yeah. Can water break apart that lattice? Yes. So we're going to get Zn2 plus 2 chlorides, and then we're left with H2 gas. And so this would be the ionic equation. Let's look at the net ionic equation. What's the spectator in this case? Looks like the spectator is zinc. Did zinc change here? Did zinc change? Yeah, on the left it's zinc metal. On the right it's zinc ion. Two totally different things. Zinc metal is a solid, zinc ion is aqueous. Did H plus change? Yeah, on the left it's H plus, on the right it's H2. Did chloride change? No, so chloride's a spectator. And so the net reaction is zinc plus 2 H pluses yields Zn2 plus H2 gas. And here, this is our reducing agent, this is our oxidizing agent, this is our oxidizing agent, this is our reducing agent, and this is going strong, strong to weak, weak. This is the single replacement reaction. For single replacement reactions, the advantages is a simple pattern. And these are fast and relatively easy. I'll just put fast and easy. Fast and easy to figure out what the products. The products are Bx plus A. It's easy. Or A plus Bx yields Ax plus B. Fast and easy. The disadvantage is it's a simple pattern. The simple pattern means A must be what? A must be the reducing agent. B must be the, and X must be the, what if they don't want to be that? What if you have, let's say you have a group of actors and they don't want to act like that. They want to act differently. So for example, A does not want to be the reducing agent. A wants to be the oxidizing agent. What's going to happen then? They should get fired. And they are. They're fired from your textbook. Your textbook is not going to allow that. Everybody has to behave. And so your textbook is not going to put in something like this, which will screw you up. Let's put in chlorine plus sodium bromide. You put in chlorine plus sodium bromide, and then we have trouble. We have trouble because this does, even though this looks simple, A plus Bx, right? But it fails. Single replacement fail. The A plus Bx single replacement, A plus Bx single replacement. And so what do you have to memorize the exceptions. Do you want to memorize all the exceptions? Your book doesn't either, and so they ignore all the exceptions. But is it a wise thing to do to ignore all the exceptions? It depends. If you never have to do it again, yes. It means less work for you. If you have to do it again, then no. No, because in nature, does nature honor those? You know? No. And nature, like for example, nature says you can't combine these two because these two will violate the single replacement form. And therefore, nature is not going to allow you to combine these two things. Is that going to happen? No, nobody's going to tell you you can't combine them. You can combine them if you want. Go ahead and combine them. You're going to get a reaction, but not the reaction you expect. Right? And so the problem here is this. The problem here is that A is not what we call a reducing agent. In fact, chlorine is a very powerful oxidizer. And And so it doesn't want to behave. And it's supposed to be the reducer, but you can't force chlorine in this particular reaction to be the reducer because it's going to be the oxidizer, and it's a strong one at that. And so in order to understand the exceptions a little bit better, we need to have a little bit more comprehensive chart. And so this is what we're going to do. Oops, I need to turn on the projector. So we're less likely to be tricked into making wrong predictions. But we should get more familiar with oxidizers and reducers. And so we're going to look at this chart. Automatically, you can kind of see this. What's lithium? Do you remember what lithium was in the activity series? What was lithium in the activity series? So the strongest reducer. So on this particular chart, we have the strongest reducer at the bottom. It doesn't matter if it's at the top or the bottom. You know, it really doesn't matter. Or if it's left or right, you know, if it's horizontally. All we know is that lithium is the strongest reducer on this chart here. Which means lithium ion is the weakest oxidizer. So what they're doing is they're ranking this based on oxidizing strength, not reducing. And so this is an inverted activity series here. So what is the strongest oxidizer on the chart? The strongest oxidizer on the chart is fluorine. Fluorine really wants electrons, more than all these species. Fluorine wants electrons. When fluorine gets those electrons, what does it form? Fluoride. So fluoride must be very stable. Does fluoride want to give up electrons? No. And so lithium is the best reducer on this chart. The worst reducer is fluoride, because fluoride doesn't want to go backwards here. It doesn't want to lose electrons. Does that make sense? Okay. And so this is what we're going to do. Now the charts are, it doesn't matter. Some charts are written horizontally. Some charts are written upside down. It doesn't matter what way they're written. You just have to memorize two things. When you use a redox chart like this, you memorize lithium and you memorize fluorine. If you memorize lithium, Li solid, and fluorine, F2 gas, then it doesn't matter how they orient it. You know, it could be in a circle. You'll always have your bearing. So some people, you know, even this morning somebody was asking me, oh, so if you go up, then it becomes stronger. Well, it depends. You know, it depends. And then they say, oh, it's going to be a stronger oxidizer. Yes, on this chart, but not on other charts. And so we don't consider up, down, left, right. We just consider lithium and fluorine. All right. So let's look at the fluorine's a very powerful oxidizer because it really wants electrons to form fluoride. So fluoride must be something stable, and it is. All right. What else really wants electrons? What's this? Let's name this. Ozone. Ozone and H+. Why do we need the H+? Well, because if ozone gains electrons, what forms? Oxide. What do you know about oxide in terms of acid-base properties? What do you know about oxides in terms of acid-base properties? Tell me one acid-base property for an oxide. It's a strong base. Yeah. I didn't make you memorize, so that's good, Chris. You remembered. I made you memorize the strong acids, but I didn't make you memorize the strong bases, did I? That's probably why a lot of people didn't come up. But oxide's a powerful base. And are powerful bases stable in water? No. Oxides are unstable. And so to help stabilize it, we form dihydrogen monoxide. Dihydrogen monoxide is water. And so that's going to help stabilize it. This is why we need the H+. You'll see it over and over again. What's this called? S2O8 2-. S2O8 2 minus is not one that I asked you to memorize, so you don't have to worry about this. In fact, this is a very unusual species. Ozone really wants electrons, so does this. But you go, why does this want electrons? It's already got a 2 minus charge. Doesn't that makes no sense because of electrostatic repulsions, Coulombic repulsions? Negative, negative, don't they repel each other? And so why would S208 2 minus want electrons when it's already got a negative charge? Can somebody tell me? Why it really wants electrons is not because the two negatives are actually, well, we have 8 oxygens. 8 oxygens. What's the charge on oxygen? Typical charge on oxygen. And that means we have 2 sulfurs. What's the charge on each sulfur? So 8 times 2 is minus 16. So this has got to be plus 16. Oh, no, not plus 16 because we've got a negative 2. This has got to be plus 14. Plus 14 minus 16 is minus 2. And so each sulfur must be plus 7. Hey, what's the maximum charge on sulfur? Based on the periodic table, what do you expect the maximum charge on sulfur? Sulfur's charge is going to range from minus 2 to plus 6. This is plus 7. So it's unusual. This is an unusual species. This is an unusual species making it want electrons. This is a powerful oxidizer. It really wants electrons. If it gains those electrons, then it goes from plus 7 to, what's the charge on sulfur and sulfate? Plus 6. Okay. And so this is why, even though it has a negative 2 charge, that negative 2 is a result of these oxygens. Are these oxygens happy with the minus 2? So for example, in dihydrogen monoxide, is oxygen happy at minus 2, or is water like, Dr. Jekyll and Mr. Hyde? Is water like Mr. Hyde? It really is going to attack things for electrons? No, so we know that water is stable. So oxygen is happy at minus 2. So we're good there. Okay, next is this. What's this called? Hydrogen peroxide. What's the charge on oxygen here? Well, hydrogen is plus 1. If hydrogen is plus 1, then that means oxygen is minus 1. Is oxygen happy at minus 1? No, what does oxygen want to be? Minus 2. And so if it's going to form oxide, that oxide is going to be stabilized by hydrogen to form dihydrogen monoxide or water. Okay, this is, what's this MnO4 minus called? Permanganate. What's the charge on manganese and permanganate? Plus 7. Can you see why permanganate's a powerful oxidizer? Is it because of the negative charge on permanganate? No, it's because of the positive charge on manganese. What is the positive charge on manganese? Plus 7, making it a powerful oxidizer. Well, we need the H+. Why do we need the H+? To stabilize the oxide. Okay, what's next? And so this is what you should do. When you have a table like this, you look at a table like this and it's too much. It's overwhelming, right? You look at a table like this. And so what you do is to make it a little less intimidating, you read through the entries a few times. After you read through the entries a few times, then you'll start seeing certain patterns. Actually, we could break this up into patterns like we did for the activity series, which we will. But over here, what is this called? Lead 4 oxide. Good. Lead 4 oxide is a solid. Okay, and it goes from lead 4 to lead 2, meaning it takes electrons or loses electrons? It takes electrons. In fact, lead 4 oxide is probably what started your car this morning, because In order, if you drove in, if you start your car, you need electrons, right? You need electricity to turn the starter motor. And so what's pulling the electrons through the starter motor? The battery. Well, what's inside the battery? Well, car batteries have lead-4 oxide. Lead-4 oxide's pulling the electrons through. Well, what's giving up the electrons? Well, lead metal in batteries is giving up the electrons. It needs 2 electrons. Those electrons come from somewhere. They don't just appear like this. And those electrons come from the reducing agent, which is lead. Okay, after lead-4 oxide comes chlorine gas. Wants to be chloride. And then, what's this called? Dichromate. This is chromium plus 6. Chromium plus 6 going to chromium plus 3. It wants electrons. We got 2 of them, so 2 at plus 3 is going to give us 6 electrons total. And so even though it has a negative charge here, the chromium is highly positive. What's this MnO2 called? MnO2 is called manganese 2 or manganese 4 oxide. Manganese 4 oxide. And so what's more powerful, manganese plus 4 or manganese plus 7? Manganese plus 7. So manganese plus 7 is going to be a better oxidizer than manganese plus 4, and that's why it's higher in ranking up here. Oxygen is a great oxidizer. In fact, that's where the name oxidizer comes from. It comes from the most common oxidizer that's around, which is oxygen gas. Oxygen gas is a pretty powerful oxidizer. Followed by, what's this? Iodate. Iodine's in the plus 5. Followed by bromine. And so we here, look here, we have fluorine, chlorine, bromine. What comes after that? Iodine. Iodine's going to be down here. And so one of the patterns that we can see is that fluorine's the most powerful. Fluorine's also the smallest. And then chlorine's bigger, bromine's bigger, iodine's the biggest. Also, fluorine's a gas, chlorine's a gas, bromine's a liquid. And so we can see little patterns like this: manganese plus 4, manganese plus 7, little patterns here and there that help us remember these. So then we go on to what's that? Nitrate. Nitrate, and we call H plus acid. Nitrate and acid. You know what nitrate and acid's called? Nitric acid. So this is nitric acid. Followed by silver ions. Silver ions turn out to be a pretty good oxidizer. They want electrons. So this is a moderate oxidizer. Followed by iron 3. Now iron 3 should gain 3 electrons, but it only gains 1 to form iron 2. And so it doesn't go all the way to iron metal, it just goes to iron 2. And then we have, hey, oxygen. Isn't that a repeat? Why do I have 2 oxygens? So this is one of the things that people who, there are a lot of people who never read the chart, not even once, and then they get confused. Why are there 2 oxygens? And so during the test, they'll come up and ask me, why are there 2 oxygens? Well, it's too late now. You can't ask me during the test. You could ask me before the test, but I'm not going to answer it now during the test. And so why are there 2 oxygens? So these are the things you want to get cleared up before you take the test. And there are 2 oxygens because, I don't know. I mean, why are there 2 oxygens here? Well, obviously one of these oxygens is more powerful, but how can one oxygen be more powerful than another oxygen? Aren't they just the same element, oxygen? And it's true, one oxygen is more powerful than the other oxygen. How is that possible? And so this, of course, this is why we read it. We read the whole thing because this oxygen forms dihydrogen monoxide, but this oxygen, what does it form? Well, what's more stable, water or hydrogen peroxide? Water. And so this is going to be a more favorable product. If it's a more favorable product, this is a more favorable reaction. Therefore, this oxygen is more favorable. Then you go, what? If this oxygen is more favorable, then let's just eliminate this one because this one's not going to happen. Well, they don't eliminate this one because it's the reducing agent. These are two different reducing agents giving the same product. So this is why there's that overlap. And so, anyway, we'll continue here. This one is going to be copper 2. Now, the interesting thing here is copper 2 doesn't gain just one electron to go to copper 1. Copper 2 gains 2 electrons to go to copper metal. When you look at this chart here, there's no copper 1. That's because, you know, if you take a penny, eventually the penny's going to turn black from oxidation, you know, old pennies. And so, in this case, when we have copper, copper is going to go to copper 2. It's not, we're just going to predict it goes all the way to copper 2, because that's what's going to happen eventually. It's going to go to copper 2. And so there's no copper 1 here. Going to, there's copper 1 in other charts. That's how we can get copper 1, but this is getting more advanced. This is called, in acid, sulfate in acid is also called sulfuric acid. So why do they do this? Why don't they just call it sulfuric acid? The reason they don't do this is because you can make this in lots of different ways. So for example, you could take sodium sulfate and hydrochloric acid. If you take sodium sulfate and hydrochloric acid and mix them together, do you know what you get? You get acid and sulfate, which is essentially sulfuric acid. The same thing with this. You could take sodium nitrate, lithium nitrate, potassium nitrate, and mix it with any acid, like HCl, HBr, HI. You're going to get this combination. And so the reason they write it like this separately is because there are lots of ways you can get it. You don't have to get a bottle of sulfuric acid. You can just get whatever you can get that mixes and gets these ions in solution, and then you have it. So after sulfuric acid comes tin 4, which goes to tin 2. Here's tin 2 that goes to tin metal. Tin 4 to sulfur, this is H+, acid, to lead 2, tin 2, iron 2, zinc 2, aluminum 3, magnesium 2. Sodium, calcium, potassium, lithium ions, ozone, hypochlorite, oxygen, water. And so at the top of this list was fluorine. At the bottom of this list is water. Is that correct? And so the strongest oxidizer is fluorine. The weakest oxidizer would be at the bottom of this list is water. Is that right? No, it's not right. Actually, at the bottom of the list is lithium ion. And so what is this? Well, this is a separate table. What's this separate table doing in my table? I don't want 2 tables, I just want 1 table. So why do I have 2 tables here? Well, if you look at the list in our classroom, in the lecture room, it's 1 table. They combine these 2 tables and make 1 table. But in this particular, this is from the Chem 1A, from our Chem 1A book, they separated into 2 separate tables. And so where do you place water then? Where you place water is based on this number here. If you look at this number, it's minus 0.828. And so we look, where does minus 0.828 go? It goes here, minus 0.828, which means water is this. Water fits between zinc ion and aluminum ion. And so water is weaker than zinc, a weaker oxidizer than zinc, but a stronger oxidizer than aluminum. That's where water fits. And so you have to get familiar. And then there are some species that are like amphoteric, but there isn't a fancy word for it. What does amphoteric mean again? It can act as either an acid or a base. Well, there's species that can act both as an oxidizer and reducer, and one of them is water. Water is going to occur on the left side as an oxidizer. Do you see it here? And water also occurs on the right side as a reducer. Here it is. Is that it? This is not it, because this is water and sulfur dioxide, so we need the sulfur dioxide there. That's not it. Water can also occur as a reducer. Let's scroll up. Is this it? No, we don't have any NO, no. Is this it? No. This one? This one? Yes. This one. Hey, but what about this one here? Do you see this one here? And this one here? Which one should I use? The stronger one. I'm going to pick this one. Why? Because we always pick the strongest one. The strongest one's going to be the one that reacts. Why do we have two of them? We have two of them because they form different products. So this one, if we go backwards, forms oxygen. This one, if we go backwards, forms, and oxygen is more stable than hydrogen peroxide. So that's the reason why. All right, so we need to familiarize ourselves, and we got to get familiar with oxidizers and reducers. And so, you know, when I come over here and I call chlorine a reducer, does that make any sense to you at all? Chlorine's one of the most powerful oxidizers on our chart. Chlorine's one of the most powerful oxidizers on our chart, and therefore the single replacement method fails because A is supposed to be a reducer. And so you have two choices. Choice one, you memorize another pattern. And so for each exception, we have to memorize a pattern. Or two, we, actually there's option three. Two is just forget about the single replacement and do a more general method. The more general method is called the chart method, where we don't have to worry about the exceptions. The chart method is automatically going to factor those in. Or three, we do a combination. You know, if we know there's going to be exception because we know things aren't going to fit their assigned roles, then we use the chart method. But if we know everything fits their assigned roles, then we use the single replacement method, because single replacement's faster, easier than the chart method. And so we just look, will things fit their roles? So let's take a look at the major fails for the single replacement. One, you know, okay, these are the fails here. A is OA, oxidizer, not a reducer. Example, chlorine, bromine, iodine, etc. Fail two, when we look at acids, we have two types of acids. We have mineral acids. Mineral acids would be like HCl. HCl would be our BX. And so H plus is the oxidizer. What about chloride? If you look on the chart, is chloride very reactive? No, chloride's quite stable. Chloride is a very weak reducer. And so it's pretty unreactive. Versus what we call an oxidizing acid. When we look at BX, X is supposed to be what? X is supposed to be spectator. And so what about nitric acid? Is nitrate going to be happy sitting around? And so let's take a look at nitric acid. A mineral acid, the anion is just a spectator, essentially, and we have the acid, H+. In an oxidizing acid, X is not happy sitting and watching. X wants to react. In fact, you know, what's more powerful of an oxidizer, nitrate or H+? Nitrate is significantly more powerful of an oxidizer than H+. And so you're the director of the play. You being the director of the play, you tell nitrate to spectate, and H+ is going to oxidize. You think nitrate's going to be happy? No. Nitrate's going to be terribly unhappy. In fact, nitrate's not going to sit around. Nitrate's going to do all the attacking. And H+ is going to be left out of the loop. And so when we're dealing with an oxidizing acid, we got to watch out because X is no longer a spectator. What are the oxidizing acids? Oxidizing acids, we like sulfuric acid. Sulfate's more powerful than H+. Nitric acid, iodic acid, perchloric acid, all those are called oxidizing acids because the anions are powerful oxidizers. All those anions, what do they have in common? High positive charge. They're all negative. Anions are negative, but the positive charge is in sulfur, in sulfate, in nitrogen, nitrogen plus 5, in iodine, in chlorine, etc. Etc. Let's see if you can figure out the etc. here. We're going to do an example really quick. Let me see. And what we can do is we'll take a break since it's break time. We'll take a break and then we'll do an example.